Okay, this is the last set of notes for Unit 2 here in Calc BC, and we're dealing with Rolle's theorem, the mean value theorem, and L'Hopital's rule. Now, Rolle's theorem, historically Rolle's theorem is important because it leads to the mean value theorem. We're not going to stress too much about Rolle's theorem, but just introducing it to make sure that you can kind of see the progression from it to the mean value theorem. So Rolle's theorem, it has three parts that have to be true to be able to apply it. So it says if f of x is continuous on the closed interval from a to b. So we're going to define an interval from a to b here, and we'll make sure that it's continuous on that interval. And if it's differentiable on the open interval from a to b, so it doesn't have to be differentiable at the endpoints. And here's the third part, here's the kicker, which mean value theorem actually doesn't have. It just has the first two parts. It says f of a has to equal f of b. Okay, so let's actually kind of, before I finish off Rolle's theorem, let's pick that out. The key is picking out an a and a b value where the y coordinates that go with them are equal. So just kind of picking it out here a little bit, let's say that a then is here, which means I want to make sure that b has the same elevation. So I'm going to say that b is right there. Okay, hopefully that's looking correct. And is it continuous on that closed interval? Yes. Is it differentiable on that open interval? You know, is it continuous in a nice smooth curve? Yes. Okay. So if all that's true, then okay, here's a symbol I do not believe I have used with you guys yet. There exists at least one C. Okay, here's another symbol, throwing lots of symbols at you guys today. Is an element of, maybe I should use a different color right there. Is an element of the open interval, a to b. Okay, and I'm just throwing all kinds of stuff at you guys today. Such that f prime of c is equal to 0. Okay, so such that, okay, getting lost with all the symbols. Then there exists at least one c that is an element of, you could just kind of say in the open interval from a to b, such that the derivative of f at c is equal to 0. Okay, and what's the derivative again? Really, it's the slope of the tangent line. So the slope of the tangent line at c is equal to 0. So the tangent line's a horizontal tangent line at that point. So as long as the first three things are all true, then we're guaranteed to have a horizontal tangent line slope somewhere in the open interval. And we can see that there is one there. So somewhere-ish about here, we have a horizontal tangent line. Okay, so yeah, that's true, and it's lovely and all that kind of stuff. But we are going to move on to the mean value theorem, which is the stronger version of Rolle's theorem, and it doesn't require that third part. It doesn't require the f of a equals f of b. But it's essentially doing about the same thing, only better. Okay, mean value theorem. If f of x is continuous on the closed interval from a to b, and f of x is differentiable on the open interval. So the first two parts are the same as Rolle's theorem, but it doesn't have that third part. So we don't have to have the f of a equals f of b, which is kind of challenging sometimes to get that, because sometimes you just can't even get that to happen. Then there exists, oh look, same symbols, but now we know what they mean. then there exists at least one C that's in the open interval from A to B such that f prime of C is equal to, oh my goodness, it's not just equal to 0, it's equal to f of B minus f of A over B minus A. Now, again, let's put it in words here. So f prime of C, that's the slope of the tangent line at C. Is equal to, okay, what is f of B minus f of A over B minus A? That seems really, really familiar. Oh yeah, that's just the slope of a line between the points A and B, isn't it? And so, in other words, it is the slope of the secant line from A to B. So I think it's easiest to remember the mean value theorem in words. As long as you have the continuous on the closed interval and differentiable on the open interval, then the slope of the tangent line is, for some C that's in that open interval, is equal to the slope of the secant line from A to B. Okay, so let's just pick out a couple points. So I'm going to say maybe here's my A. So notice I'm not even picking out the points on the curve first. I'm just picking out A and B and just making sure that it's continuous and differentiable on that interval. Okay, so which it is. We can see it is. Okay, so remember it says the slope of the tangent line is equal to the slope of the secant. Well, let's draw on the slope of the secant line. Slope of the secant line, it's going to go through those 2 points. Hopefully I draw this fairly straight. Here's my secant line. Okay, and there's at least one C where the slope of the tangent line will equal that slope of the secant line. Now, there could be more than one in that open interval. I think I can see at least one here, so it looks like about right here. We get one. And it looks like we also get another one right about here. And so it's possible to have more than one. Now, it's more than likely you're just going to get one. But you're guaranteed at least one. Guaranteed at least one. Okay, and just all kinds of applications for mean value theorem. Okay, we're not going to get into all the applications in this notes, but we're just going to go ahead and do it. We're going to solve for C on a couple of these. Okay, so given the function f of x equals root x minus 1, which, by the way, it's like we need to know if the mean value theorem even applies. So the vertex is at 1, 0, and this one is a half parabola opening up to the right. And my my interval is from 1 to 7. So I would say that that's fairly safe that mean value theorem applies because it's going to be continuous and differentiable on that interval. Okay, and so for example, even if I did 1 and even let's just say 7's here, and draw in the secant line, then we can even see that there should be some point-ish in here where the slope of the tangent line will equal the slope of the secant line. Okay, but we're not trying to do an approximation here. We're trying to actually calculate it. And so let's remind ourselves, okay, so the slope of the tangent line at C, slope of the tangent line, derivatives, they, that's the slope of the tangent line. So f prime is is 1 over 2 root x minus 1, and the derivative of the guts is 1. So there's my slope of my tangent line for any value of x. And I need to calculate the slope of my secant line on this closed interval. So f of 7 minus f of 1 over 7 minus 1, which is, okay, so if I input a 7, I get root 6. If I input a 1, I get square root of 0, which is 0. And 7 minus 1, so I get root 6 over 6, which is rationalized, but we could also write it 1 over root 6 either way. So what did we say the mean value theorem is, as long as it applies, which it does here? The slope of the tangent line is equal to the slope of the secant line. Okay, and so we can set those two things equal to each other and solve for the c. Now, you can actually plug in a c for the x right here and then solve for c, but you don't have to plug in a c for the x. You can just set these two things equal and then solve for x, and that will be the c value that's in there. So 1 over 2 root x minus 1 is equal to 1 over root 6. Okay, and let's see, if we cross multiply here, we get root 6 equals 2 root x minus 1, and I could square both sides. Okay, and so I get 6 equals 4 times x minus 1, so 6 over 4, 3 halves, plus 1 is equal to x, which means that x is equal to, what would that be, 5 halves. So that's the c. c is 5 halves. Okay. And notice that 5 halves is in that open interval between 1 and 7. Does it seem reasonable? 2.5? Yeah, you know, I mean, there's 1. That seems reasonable that could be 2.5, about even just where we were just kind of approximating. Okay, problem number 2. Given the function g of x, find any c using the mean value theorem if it applies. So we better check it out. Let's see. Vertical asymptote at x equals -1. There is a horizontal asymptote at y equals 1. And let's see, we'd have an x-intercept at +2. And if we plug in 0 for x's, we get the y-intercept of -2. And so it must have a piece down here. And there are no other x-intercepts, therefore there must be a piece over here. Okay, now there's a vertical asymptote, so it's not continuous at x equals -1. So -1 had better not be in our interval that we're looking at, because if -1 is in our interval, then the mean value theorem doesn't apply. But as long as we're to the left side of the vertical asymptote or to the right side of the vertical asymptote, it's going to be a nice smooth curve, and the mean value theorems apply. So the interval is from -2 to -5/4, which is, let's see, -2 to -5/4. -5/4 is just to the left of, so yes, it applies. Okay, so let's see, we need the derivative. So g prime of x. So low d high minus high d low all over low, low. Okay, so we have x plus 1 minus x plus 2, and so our derivative is 3 over x plus 1 quantity squared. Okay, so that's our derivative. we need to get the slope of our secant line, which we're going to be doing g of -5/4 minus g of -2 all over -5/4 minus a -2. Okay, maybe the hardest part of this problem is just calculating all this right now. So -5/4 minus a -2, so that's -5/4 plus 2, so it's -5/4 plus 8/4, which is 3/4. Okay, g of -5/4. A little bit of scratch paper here right now. So g of -5/4. Okay, so I've got -5/4 minus 2, so that's -8/4 over -5/4 plus 1, so that's plus 4/4. So really that's -13 over -1, which is 13. Minus, okay, now I need g of -2, g of -2, which is -2 minus 2, over -2 plus 1, which is -4 over -1, which is 4. Okay, 13 minus 4 is 9, and so, which is 12. Okay, so the slope of the tangent line will be equal to the slope of the secant line at least one time. Maybe no more than one time, but at least one time somewhere in that open interval. Okay, so if we set those two things equal to each other, and so I can get 3 equals 12 times x plus 1 quantity squared, and 3/12, 1/4 is equal to x plus 1 quantity squared, and so we can get plus and minus 1/2 is equal to x plus 1. So x is equal to -1 plus and minus 1/2. Okay, so we have possibilities here of -1 plus 1/2, which is -1/2, and -1 minus 1/2, which is -3/2. Now, -1/2. -1/2 is on the right-hand side of the vertical asymptote, which indicates it's not in that interval from -2 to -5/4. So this one gets thrown out because it is not in the open interval from -2 to -5/4. So if you ever, I mean, sometimes you'll get more than one possible answer, but if it's not in the interval, you have to throw it out. Even if it lands on the endpoint, you actually have to throw it out just by the rule. -3/2 is in the interval, and so therefore this is our C. C equals -3/2. Okay, so that's mean value theorem, which also Rolle's theorem leading up to it. Okay, and finally, L'Hopital's rule. Okay, now there's a whole lot written about it, but we're gonna try to keep it fairly simple here. L'Hopital's rule is incredibly helpful for us, and yes, it does look a bit like hospital. In fact, it's French guy that the family had a lot of money, and he enjoyed mathematics, so he actually helped sponsor some mathematicians. You used to have rich people who would sponsor artists, you know, painters, stuff like that. He enjoyed math, and so he sponsored mathematicians. And so, anyway, he's not the actual one who figured this out, but one of the mathematicians that he was sponsoring figured this out. So he got to put his name on it, though. So it helps us a lot with limits here. So if limit as x approaches of a fraction, it has to be a fraction. So f of x over g of x. If you get 0 over 0 or infinity over infinity, these are two indeterminate forms that this works for. Okay, there are many other indeterminate forms, but if you get either 0 over 0 or infinity over infinity, then what you can do is you can actually take the derivative of the top and the derivative of the bottom and reapply the limit. Okay, now by the way, L'Hopital's does not take care of every type of limit, so we still have to be able to do the other limit things that we've learned. But it is incredibly useful. Okay, so let's do some examples here. So limit as x approaches 0. Now I notice immediately that my denominator it would be 0. So I'm going to start checking to see if my numerator is 0 also if I try to plug in the 0. So if I plug in the 0, I get square root of 1 minus 1, that's 0, minus 0 over 2. Yes, it is 0 over 0. Now, it is very important that we actually advertise what is going on, but do not say equals 0 over 0 or infinity over infinity. It's important not to say that something is equal to an indeterminate form, an undefined form. But just above the equal sign, we're going to write the indeterminate form that it was 0 over 0. And then we're going to write down comma and the fact that we are applying L'Hopital's, but we're going to abbreviate just a little bit. So LHOP. So we've advertised what we're doing now, so now we're going to go ahead and do it. So limit as x approaches 0. Keep writing limit until you actually take the limit. But what does it say we get to do? We get to do the derivative of the top over the derivative of the bottom. It's the thing that everybody wishes the quotient rule was, but it's not the quotient rule. So the derivative of the bottom is 2x. Derivative of the top is a little bit more complex. So obviously the square root of 1 plus x, that's 1 over 2 root 1 plus x. Derivative of negative 1 is 0, and the derivative of negative x over 2 is minus 1/2. Okay, now we can see the denominator is still 0. The top is kind of a mess too, but what if we just plugged in? I mean, if we plugged in a 0 to the top, don't we have 1/2 minus 1/2, which is also 0? Yes. Okay, so now the cool thing here is we can repeat this as long as we're still getting 0 over 0 or infinity over infinity. So that's what we're going to do. It might be kind of nice to maybe clean up the numerator some. Here's another way you could do it, because what's really happening with the 1 over 2 times the square root of 1 plus x, isn't this really 1/2 times 1 plus x to the negative 1/2? And so you could just kind of think of it that way. Or you could also clean it up, multiply top and bottom by 2 root 1 plus x. So maybe I'll go ahead and do it on this way on this one, but you'll see. So we get, so I'm not writing equals 0 over 0 right now because I'm just going to do some algebra cleanup. But I do write the limit again because I haven't taken the limit yet. Now I do get 1 minus and root 1 plus x all over 4x root 1 plus x. Okay, now we do still get 0 over 0. So we get 2 again, so I'm pointing that out. I'm going to go ahead and do it. So I've got the limit as x approaches 0. Now the top, we get negative 1 over 2 root 1 plus x, and the derivative of the x is 1. The bottom, unfortunately the bottom, maybe I should have done it the other way. The bottom, we're going to have to do the product rule. So I've got the first times the derivative of the second, so 1 over 2 root 1 plus x, plus the second, 1 plus x times the derivative of the first, which would be 4. Okay, well, let's see. If we plug in a 0 right now, do we get 0 over 0 again? Well, not in the top. So in the top, I am getting negative 1 over 2. So as soon as you're not getting 0 over 0 or an infinity over infinity, you're done. You just have to clean it up. So we're going to be done here on this one. Now, I've got two things in the denominator. The first part here is 0, but then there's a plus, and then I have 4 times the square root of 1, which is 4. And so negative 1/2 over 4, which is negative 1/8. Okay, now that was a really, really tough limit, and it's one of the harder ones with L'Hopital's, but gives you an idea to see what we can do. Let's try some others here. Okay, so the limit as x goes to 0 of x minus sine x over x cubed. So right now the denominator is 0, so I'm checking the numerator. 0 minus, yep, L'Hopital's. But I don't really have space there, so I'm going to go down here. So limit as as x goes to 0. My denominator is 3x squared. My numerator is 1 minus cosine x. And so I'm still getting 0 in my denominator, so I'm checking my numerator. 1 minus cosine of 0, that's 1 minus 1. That is 0 over 0 again. So I get to apply L'Hopital's rule again. And so I get sine x over 6x, which that's 0 over 0. And so we get the limit as x approaches 0 of cosine x over 6. Oh, my denominator is just 6. So I'm going to be done here. What's cosine of 0? 1. Okay, well, that's pretty cool. Okay, limit as x approaches pi over 2. Tangent of pi over 2. Well, we normally just think of it as undefined, but graphically, what's going on with tangent as it goes to pi over 2? Isn't it going to infinity? So let's check the denominator as well. 1 plus infinity. Well, 1 plus infinity is also infinity. Okay, and so, oh, look, that's another infinity over infinity we can apply L'Hopital's. So limit as x approaches pi over 2. Well, what's the derivative of tangent x? Secant squared x. Derivative of 1 is 0. Derivative of tangent x, oh, secant, oh, that's just 1. By the way, just in case any of you are worried, it's like, what is secant of pi over 2? Well, what's cosine pi over 2? Well, let's not worry about it. This one is 1. This is 1. Finally, we come up on limit as x approaches infinity, and it's not even a fraction. Okay, so if it's not a fraction, probably, and by the way, I remember I told you that L'Hopital's doesn't work for every single type of problem, but it does for all these examples. So I'm just trying to show you some good examples. But this is not even a fraction, and if we check the infinity, this is looking like, let me change colors here. This is looking like infinity times sine of 0, which is 0. Infinity times 0. So it's not, this is not 0 over 0, it's not infinity times infinity over infinity, but it is another indeterminate form. So 0 over 0 is 1, infinity over infinity is another, 0 times infinity or infinity times 0, even 1 to the infinity. Now, you know, if it's truly 0, I mean, if it's literally 0 times infinity, and 0 times n number is 0, but the sine of 1 over x is just approaching 0. Just like if you have 1 to the infinity power, if it's truly the actual number 1, 1 to any power is 1. But if it's just approaching 1 to an infinite power, it's an indeterminate form. So you go, okay, well, what's the problem here now? Okay, well, can we get it so it's a fraction? Can I move either the x or the sine of 1 over x? Well, we should be able to, it's a product, so we should be able to move one of them into the denominator. I would say typically it's not a good idea to move the trig. I mean, we could say it's x over cosecant 1 over x, that is possible, but I'd just say typically it's not a good idea to move the trig. So, limit as x goes to infinity, if I move the x, it becomes 1 over x. Now, I kind of like that because the 1 over x is the same as the angle in here. But let's check it out. So as x goes to infinity, this is becoming sine of 0, which we know is 0, approaching 0 anyway. And 1 over x, well, that's approaching 0 as well. So guess what? We get to apply L'Hopital's now. So the limit as x goes to infinity, so cosine of whatever the angle is, the angle does not change, but the derivative of the guts is negative 1 over x squared. And then what's really nice is, because they are the same, you know that the derivative of 1 over x is negative 1 over x squared down there as well. And those two reduce. And so you're just left with cosine of 1 over x, taking the limit as x goes to infinity, which is cosine of 0, which is 1.